Morning to Dr. Aida. Today we would like to do our project presentation. First of all, let us introduce ourselves. My name is Lee Song Tin.
My name is Mo Sheng Han from Group 5.
My name is Leong Zi Wei.
My name is Tong Kang Chun.
Problem background. The cavern is filled with water until its maximum level. Therefore, the electrical pump is needed to install at the cavern. The issue is faced when the cavern is in dry condition, but the motor is still running, so we have to manually turn it off. If the motor is still running without turning off manually, the pump will fail and cost a lot to fix it. Besides that, this is the details of proposal instrumentation. In the housing, there are some devices such as transmitter, controller, analog digital converter, and digital analog converter. The motor and level sensor are installed in the cavern.
And now I'm going to talk about the working principle of this project. When the water is filled up to maximum level, the level sensor will detect the condition and send a signal to transmitter. And before the signal transfer to the transmitter, it will be converted from analog signal to digital signal. The transmitter will accept low electrical signal and format them so that they can be transmitted to a distant receiver. After that, the signal will be sent to the controller, and the controller will process the received signal and giving an output. And the output given by the controller is in digital signal. The digital signal will be converted into analog signal before the signal transfer to the pump. Once the pump receives the signal from controller, the motor of pump will start to pump the water from the cavern.
This is the similar example of transfer response. This transfer function is similar with our project. The transfer function is 25 divided by s power of 2 plus 5s plus 25. From this transfer function, we can know that the peak time, settling time, and also the percent overshoot. In this transfer function, the peak time is 0.726 seconds and the settling time is 1.6 seconds. The percent of overshoot is 16%.
Now, I'm going to talk about how to ensure stability of our system. A linear system is stable when it is able to give the same output when used to measure a constant input over a period of time. When poles are located on the right half of the complex S-plane, right half, the system is unstable. When poles are located on the left half of the complex S-plane, the system is stable. A marginally stable system has poles located on the imaginary axis. There is another way for us to ensure the stability of our system. We can find the range of gain, which is K, for the system below that will cause the system to be stable, unstable, and marginally stable. First, we consider this as our closed-loop transfer function. Then, we use Routh-Hurwitz criterion to construct this table. We fill in the first two rows of the table with the coefficient from the denominator, which is known as characteristic equation. After that, we fill in the rest of the table with the modified determinant formula. Then, we can determine the value of K for stable, unstable, and marginally stable system. That's all from me. Thank you.
Next, I will be talk about the steady state error. We can define the steady state error is the differences between the input and output of a system as time goes to infinity. For instance, when the response has reached to the steady state, now we see the right of the bottom of the slide. We can saw a graph which is end of the line is constant, which means that steady state error is occur. For the next slide is an example of the system GX. At the bottom, we have one example of a system. We can say that what type of R that insert to the system, there will be produced a write C, which means output. Based on the graph, it shows position against time. They have three types of test signal, which is first step, the constant position. Next will be the ramp. The graph is increases linearly, which is a constant speed. Last will be parabola. It shows the constant acceleration line on the graph. Next will be the steady state error for unity feedback in terms of closed loop transfer function TS. Based on the figure below, it shows unity feedback because it has a negative. Actually, it has a negative sign at the closed bottom, at the closed circle bottom, and positive sign is above the closed circle above. And the R is represent input and C will be represent output. C will be compared to what we measure, which means C will be given us error. We can do some analysis for the steady state error through a closed loop system. Can be obtained as following. First step is EX equal to RX minus CX. Second step will be C equal to R times T. Actually, the basic formula is T equal to output over by input. And then the step 3 is substitute equation 2 into equation 1. And step 4 will be applying the final values theorem. And the fifth step is a substitute equation 3 into 4. And next will be the steady state error for the open system. First will be, actually it's a very similar to the closed loop system, and first is a step input Rx equal to 1 over x, and the ramp input is Rx equal to 1 over s squared, and then third one is a parabolic input Rx equal to 1 per s cubed. Actually, three of these already shown in front of the graph that show have a step, ramp, parabolic. And then next slide will be the static error constant. Steady state error perform specification for negative unit feedback system are called static error constant. Position constant is Kp, and velocity constant is Kv, and acceleration constant is Ka. And all of this is already shown in front of the graph and can the figure in front and can see for the picture. And then next is the relationship between input, system type, static error, constant, and steady state error. For the steady state error formula have 1 over 1 plus Kp. Next will be 1 over Kv, and third one is 1 over Ka. And this 4 is very important. And next I will be say thank you for watching our presentation.